So far, our discussion has considered the crystal structures of various materials, and also we just covered their locations and directions, and we are able now to identify locations and directions vectors in these cells using three integers or indices for their description, and using four sometimes for the hexagonal close packed directions. We'll now consider planes within these cell structures. So we're going to use indices again, three of them, but now we're going to consider primarily the intercepts of this plane. So remember, we're looking at the intercepts for a plane. Then we're going to make it nice and clean using no fractions and common multiples. So, and then the planes themselves are easy to identify in terms of their families, because if they're parallel, then they'll have essentially the same Miller indices. For an algorithm, the first thing we're going to do is read off the intercepts again of a plane with the axes in terms of those plane parameters A, B, and C. So remember, we're looking at the intercepts first. Then we're going to take the reciprocals of the intercepts. And then we're going to make them into the smallest integer values. Then we will enclose them in parentheses without the commas, just like we did before. But these will be in parentheses. Remember, that's for the planes. Planes, parentheses. So what does that look like? Here we go. If you'll notice, this 001 plane is 001 because, if you'll notice, it never intersects the x-axis. Now, this one does intersect the x-axis, but along its entire length. So that doesn't mean anything. It's kind of like the undefined. But if it's undefined, we can also consider it, from an engineering standpoint, effectively infinity. So we find a parallel plane up here so we can understand it better. And this always is parallel with that x-axis, so it never intersects it. Same thing with this y-axis. So we consider the intersection for the x and the y infinity. And it does intersect z here at 1. So my next step, as I indicated before, was to take the reciprocal, or the inverse, of each one. And effectively, although not mathematically, you'll have mathematicians growling at this, but effectively, from an engineering perspective, if I divide 1 by a much, 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 much huger number, I effectively get 0, 0, 1. And I make sure that my fractions are all in most simplified terms, and that we have integers, and I put them in these parentheses. And that's how we end up with a 001 plane. Notice that each one of these planes is also parallel to the other. So even though this one might be 001 bar, that's fine. It's still an equivalent 001 plane. Here we have a 110 plane. So how did we get this? Well, this plane, if you'll notice, it intersects x at 1 and intersects y at 1. But it is parallel and never intersects the z-axis. So we will write this as the intercept of x is 1 and the intercept at y is 1. And it is parallel to the z, so we write that as infinity. We take the inverses, and we simplify, and then we put them in parentheses, and we end up with a 1, 1, 0 plane. And each of these are also equivalent. You could say that this would end up being a y-intercept of 2, but then this would go all the way over here to x and intercept x at 2. So let's see if I can make that a little better. Okay, y is 2, x is 2, so we would end up with 2, 2, and then it would still be parallel to z. This plane's parallel to z. So infinity, and then I take the inverse, 1 half, 1 half, 1 over infinity, and then I would multiply through this time by 2 because I have fractions and we don't want fractions. So multiplying through by 2 would give me 1, 1, and 2 times 0 is still 0, and then we put it in parentheses. So we have effectively the same plane as here and here. So in a very large group of these cells, as you would have in any given solid, you can have these same effective planes. It doesn't really matter that much which one you're looking at. They will act roughly the same. Here we have a 1, 1, 1 plane. And this one should be easy for you to identify. We have the x-intercept is 1, the z-intercept is 1, and the y-intercept is 1. So I have 1, 1, 1, and I take the inverses, and that ends up being 1, 1, 1 again, and I just put those in parentheses. And so that's a fairly easy calculation to make. So here's some more examples as I just went through. The 1, 1, 0 plane. And here's a slightly different plane. We've got, along the x-axis, we've got half an A here. So right there, half of an A. But it's parallel to both y and z. So this is parallel to z, and that's parallel to y. So those are both infinity, or undefined. So our reciprocals end up being 1 over a half, which ends up being 2. Of course, the 0 and the 0. And now we have a simplification down to the simplest integers. And in fact, we can divide everything through by 2 and still have integers. So we end up with 1, 0, 0 right here. And that makes sense because this is a parallel plane to all the other 1, 0, 0 planes. Here's something a little bit more complicated. We go halfway to A in the x-axis, all the way to B in the y-axis, and 3/4 of the way to C along the z-axis. Now what do we do with this? So this is a plane defined by 3 points. We take the reciprocals. Obviously the inverse of 1 half is 2, 1 is 1, and we end up with 4/3 here. So now we have to multiply through by 3 so that this becomes an integer. So 3 times 2 is 6, 3 times 1 is 3, and 3 times 4/3 is 4. And those are our Miller indices, 6, 3, and 4. Now you can have a family of planes, especially it's easy to make it if it's cubic. So the 1, 0, 0 will be the 0, 1, 0, and so on and so forth. And if we have a family of planes, we enclose them in brackets. So brackets will enclose planes. An individual plane will be in parentheses. Basically the same idea. We look for the intercepts. This one you can see clearly intercepts A1 right here, A away from the origin. It also intercepts A3, but it's at a negative A from the origin. So this is backwards here. And A2, it looks, notice how it has a line going from this edge to that edge. That's parallel with A2. So A2 will be 0. Oh, and also it intersects Z at the value of C. So we have A1 here, A2 it is parallel with, A3 it's negative 1 back here. So again, here's how it goes back from A3 minus 1, because this is the positive A3 direction. A2 runs along this direction, and that's parallel with this. So this plane will never intersect A2, so we have an infinity here. And A1 is most easily seen here because it's one unit vector away from the origin, so we have 1 here. Okay, from these intercepts we get the reciprocals, as we've already gone through, fairly straightforward. We simplify, also straightforward, and then we put them in the Miller-Bravais parentheses. Using the 4 indices of the Miller-Bravais system helps to more consistently label these types of planes and directions, and it's very helpful and descriptive of these directions and planes. Now I'll show you a few more of these planes. This is the 0, 1, 1 plane. So if you'll notice, it intersects Y and Z both at 1. So that's 1 and 1, that's the inverse of each, but it's parallel with the X. So will take an infinite distance to intersect X. So the inverse of infinity is effectively 0, and the inverse of 1 for each of these is 1, so that's why that's the 0, 1, 1 plane. Let's look at the 1, 1, 1 bar plane. So it intersects each one of these planes, Y, X, and Z. Intersecting Y at 1, X at 1, and Z at negative 1. But don't forget, we need to take the inverse of each first. That's how we find the indices. Okay, so let's see what this looks like. So we've got more planes here, and then we have some parallel planes that you can see. All right, let's look at the 201 plane, and we can get 201 by, again, following these rules. First, I look at my intercepts. Along the x-axis, I intercept at 1/2. Along the y-axis, notice how I have simply a plane that's parallel to the y-axis. And again, if for some weird reason it intersected the y-axis along its entire length, just remember we just need to find a parallel plane and it will not intersect it at all. So it never intersects y, or it takes forever to intersect y. And in Z, it intersects at 1. So now I take the inverse of these, 2, 0, 1, and then I find how I can make this into the smallest integers, and they're already there. And I put them in parentheses, 2, 0, 1. And that matches up with what we've got there. If I want to show this in an expanded plane, from here down to here would be -2 for Z, but I can also look at it from this direction, and it could be -2 for z and -1 for x, and still parallel to y. So we'd still end up with 201. And let's make another plane. See, here's a parallel plane. Doesn't matter. We still just need to choose the origin carefully so we can make easier calculations. So this is the 1 bar 3 0. So I'm going backwards with x by 1 full unit, and I'm going 1/3 of the way with y, and in parallel to z. So -1 with the x, and 1/3 with y, and it'll take a long time to get to z. I take the inverse of them. There we go. And I put it in the proper notation. And these integers up here are in the most simplified form. So if I'd had 630, I could divide evenly by 3 and I'd end up with 210. But I don't have 630. I got 1 bar 3 0 in the simplest form. And there it is with the expanded plane and a parallel plane with it. Finally, 3 2 1. How do we get 3 2 bar 1 plane out of this? Well, it goes along x about 1/3, goes along y about -1/2, and it goes along z a full 1. Take the inverse, 3, -2, 1, and these are already in the simplest format, so I put it into our proper notation, 3 2 bar 1 in parentheses. Looking at an expanded plane, it's very interesting this way in this cube. And I'm going to add another one here that's parallel to it, like that. Now we have discussed the different cubic structures, calculations involving them, directions, locations, and now planes, and how to calculate them and characterize them using standard indices. And again, we don't have any particular dimensions or units on here, just it's very generic for any of the crystal structures.